Record. It is recording. Sweet. So I have basically just an empty Scala project to start with, and we're going to talk about a data structure that is used as an implementation detail mostly in the ZIO framework that we're all probably familiar with. I will go over, though, at the start, some motivation for why this exists and why it's interesting and cool, and then we can implement it ourselves. Maybe at first we can actually just talk about what has is and what it does. Just a very simple example. So I'm going to import ZIO.has. It's a data type in ZIO that we can just import at the top level. And let's talk about how you construct a has. You just use its apply method. You could put a type in there. So I'll make a has of int. So here we're going to get back a has of int. Whatever value. Yeah.
You may want to share your screen.
You can't just see the reflection off of my glasses, Rob? Wait, it's not good enough for you?
I can, but it's hard.
Oh, you guys need better monitors. I'm a fool. Okay, let's that was I got carried away. Okay. I'm gonna keep that. And let's, because all I did is this. So now here's the grand reveal. I have an IntelliJ project, and I have a file. I've imported ZIO.has, and I've made a has. Cool. Yeah, let me know if this is too big, not big enough, etc. Thanks so much, Rob, for letting me know that. You can construct hases. We don't know yet why you'd want to do this, but we can put values in them like this. Nice, we have a has of int. Whoop-de-doo. We can also do that with another value. So let's make a has of string. I'm just going to throw some thing in here. Hello. Type that as well. And then the cool thing is that you can combine them. So I'm going to make a combined here, which is going to be int plus plus string. Then we will have IntelliJ spit out the type annotation for us. And we can see that it's kind of interesting. It is a compound type, an intersection type, a width type. It is the width of both individual hases. So right now, okay, cool. We just know how you can combine two things to get another type, but how do you actually use them? Well, you kind of use these like a map. We can get values out. So we can say, whatever, out int. I can say int.get, and this will get me the int out. I can say string, out string. I can say string.get, and this will get me a string. And then the cool thing is if you have combined, out int2, I guess I'll call it, I'll use combined and I'll call get on it. And then get actually takes a type parameter. It was inferred here because these were only single hases, but if it has multiple things, if it's an intersection of hases, I can now decide whether or not I want to get out the int or whether or not I want to get out the string. So just to show really quickly, I can make a main function here, a main method, and I'll just take this, plop this inside, call print line, and then I will run this. And we'll see when I call combined get string after it compiles for the first time. So there we go. So it says hello. So we got the hello out of this combined type. And if I say, obviously, get int, we will get out the int. So if this reminds you of a certain data structure, that's probably going to be a map. The understanding that I like to tell coworkers is that you can think of has as basically a map where the keys are types and the values are implementations or instances of those types, members of those types. So this is just like a map, except at the type level, we're able to know exactly what types are in that map and then retrieve them. And that's nice because you get compile time safety. If you try to access something that's not in a map, unlike the usual map, it knows exactly what types it has in there. So this just will not compile if I try to get something that is not in that map. And it gives me a warning here saying cannot prove that has int with has string is a subtype of has boolean. And we can see why that shows up in a minute and why that's the error message. But yeah, that's has, that's the API of has. And if you've used ZIO and you use ZLayers, you'll know that ZLayers also have a plus plus operator on them. And it behaves quite similarly. You don't get back a has, obviously, you get back a ZLayer, but there's a has nested inside of ZLayers. It's sort of an implementation of detail of them. So why, I guess another step to talk about is why even have this? I mean, it's definitely cool, but what is the actual motivation why were hases invented? And that's because, and we could turn to actually ZIO for a moment here. So let me import all of ZIO and extend app. And then I will implement the run method here. Nice. And I'll have some program equals, let's just say for now, ZIO dot environment int. So we have a program that has an environment of an int. When you call ZIO.environment, this gets you back something like this. It gets you back a ZIO that in its environment parameter requires an int, and then it spits it back out as the result type. So you can add some environmental dependency to this ZIO, and it's going to be whatever type you put in here. In order to run this program, in order to call program.exit code here, I'm going to first need to feed it an int, because that's its requirements. So in order to do that, you call a function called provide, and you have to give the environment of the effect. So we need to first call it like, it's kind of like a function. This is the input. So we need to give it the int. So I can say provide 12, and now it will run. And I could say something like, flat map results, and I'll just do this hacky thing, print line of results, so we can see what we get back. Now I can run this effect, and we get 12. So hooray. This simply wanted an int in the environment, and then we got it back. And then we can map over this, multiply it by 2 or something, and then run our program, we should get back 24. The nice thing about this environment parameter in general is that you can sort of say you want something in the environment and then not have to worry about how you're going to get that. So we want some int, and we just don't care right now where we get that int from or what int it is. As long as it behaves like an int, we're going to use it. We can multiply it by 2, and only at the end of the world, or really at any stage, any higher level, we can satisfy that dependency by calling provide, which gets us back a program where this is any. It satisfies the dependency. So that's one interesting bit of ZIO. But then there's also, we could have a second program. So we can do the same thing except with string, let's say. Except this time I'll just take the string and I will append some exclamation points to it. Okay, so if we call program 2, now we'll have to say provide a string. And so we'll get hello, bang, bang, bang. Also just a warning, my cats are now trying to climb on me, so they might appear at any moment. Okay, so that's the same thing, but for program 3, we can call program zip program 2. We can zip them together, and one of the reasons why we refer to ZIO as composable, it's because it intelligently sort of combines all of these parameters. So the output types get combined, they get tupled up. So we're zipping the outputs together. And then how do you combine the input types? Well, the best thing that you can really do is with them together. Unfortunately, because our types here were these primitives, like string and int themselves, that becomes a little awkward because you cannot actually make a string with an int. There's no way to now call program 3. We'd have to make something, we'd have to provide it something that is string with int. And these aren't traits you can extend. You cannot satisfy this interface. In order to satisfy this before ZLayers, what you ended up needing to do was make some traits. So we might say has int. And then this would have an int method that can get you the int back. And then we can have string, which would get you a string back from a string method. And then instead of this, we can ask for a has of string. And then I could call something like, oh, I should say int. This should be a has int. This should be a has string. And then I could call dot string on this. Regenerate the types, regenerates. So now it is has string with has int. And unlike string with int, we can actually create one of these. So I could make something like a new has string with has int. And I can provide some values here. So 12 and hello again, I suppose. And now I can run this. I've provided the dependencies. And we get a tuple probably of 24 and hello, bang, bang, bang. It's doable, right? This was kind of the first version of ZIO's environment. This was kind of the pattern that was recommended. There's some difficulties. For instance, if this also had a string method that you wanted to behave differently, you had to go through some extra layers of boilerplates. You had to be careful not to collide in these namespaces. And also, you have to basically build a new one every time. If you had another function that had a has boolean, you couldn't just use a pre-existing definition of has string with has int elegantly. You basically have to redefine everything. It just wasn't it was composable at the type level. It was sort of technically composable, but it required too much machinery for actually building up those intersection types with traits. There was a better way. And I don't know who decided to do this, but some genius came up with the idea of has. So we can delete this. So the idea is to go back to the original version. That was nicer, right? That was nicer to use. You had an int, you had a string. We couldn't provide this. But yeah, you get to say exactly what you want. You don't have to make some intermediate trait. But obviously, there's going to be some machinery involved. So instead of calling environment, we can call service. And what service is going to do is going to get us a has of that type. So it's just like environment, except it wraps the dependency in a has. And then I don't even need to call .int any longer because it gets us back. It both, if I look at the implementation here, you give it a type, it gives you a URIO, so an environment that needs a has of the type, and then it just gets the type back for you. It extracts it from the has. That's where the power of has comes in. It allows this sort of, maps, you can think of them as sort of a version of combination. You can combine things for free. Two different values you put in a map don't need to know about each other. They just need to be stored under separate keys. And that's kind of the intuition here. You don't need to build some super type that meets all these interfaces. The implementations of these individual hases can be completely independent. And that's where layer comes in. So I can have a string layer, and I could say ZLayer.succeed, give it a string, hello. And then I can have my int layer, ZLayer.succeed of 12. And then I can have my sort of combined layer, which is going to be string layer plus plus combined layer. And if we add the types here, we'll see like this is where that has combination comes in. This is how it's all connected. Yeah, so this gets us back a layer that has the outputs. Ooh, not quite. I screwed something up. Oh, I'm combining it with itself. Int layer. Try that again. Okay, so this is a U layer of its combination. So it's has string with has int. And as we know, now we can call get on this, passing in the individual type. So it's able to internally now separate out the requirements and thread them along through the program. So now all we have to do is, instead of calling provide, we call provide layer, pass in a layer that has the environment, and this compiles again. And it's now composable both in theory at the type level, but also in practice. It's easier you can write a definition for one layer, another definition for another layer, and then combine them together in this way. And string layer doesn't need to know anything about int layer. And also there's this sort of ability to provide dependencies with layers as well. So this version, might need a has of Boolean to get you a has of string. We're not going to get into that right now. That's kind of the power of layers. But has, clearly, that was the pain that drove the implementation of has. And we could obviously inline this as well, and it wouldn't be too bad. And it's simpler than the trait definition, and it grows, it extends a lot more nicely. So I'm going to pause there and just see, are there any questions? Obviously, we're going to get into how has works, but does it make sense what the pain was that motivated has?
Yeah, it makes sense.
Okay, cool. So that was that. Now, how do we implement has? That's why it's kind of cool, right? It seems it's pretty fancy. How do you get things out? How do you make the type safe? How does all of that work? So let me make maybe a new file. I'll make it a case class. So we'll call it has, and we're not going to import ZIO. So no ZIOs has, we're just going to do this all by ourselves. And we're going to make a companion object, and we're going to make a little main function here that we can write a little test in. What we want to be able to do is to have the same thing as before. We want to be able to put an int in a has and get back a has of int. We want to be able to put a string in a has and get back a has of string. And then we want to be able to, and then we also want to be able to combined has, which is going to be a has string with has int. And then this would be the result of calling int has plus plus string has. And finally, we'd like to be able to get values out of the combined has. So I should be able to say combined has.get of int, see the int, combined has string, see the string we put in there, and then also say Boolean and have this not compile. Obviously, none of this is compiling right now. Let me make this slightly smaller. And basically, I'm going to start from here, and we'll slowly unlock capabilities. So clearly, we want a way to take a value and put it into a has. So we're going to want something like this. We're going to want to have a function, just apply, that's going to take some value of a and get us back a has of a. That's kind of the pattern here. We don't know how we're going to implement this. Clearly, has needs to have a type parameter, so we're going to give it an a there. Okay, this type checks just because we're lying. How has is implemented is basically that intuition that you might have had, which is that this looks just like a map. Well, that's the guide to the intuition. There's an underlying map. We'll just call it map for now, which is basically a map from, we could just simplify it and make it a map from strings to any. It's not very type safe at this level. We're going to make sure that this is a private member of this. No one can access this map. This is purely an implementation detail, but really this has to be a map on the inside. The type safety is going to come in only, it's only going to live at the type level at the compile, I mean, like normally with types, but they only live during compilation. But in this case, it's probably, it might feel a little more extreme than usual. We're going to be lying a lot, sort of lying. Let's see what I mean by this. So we have a map from string to any. So how do we call apply. How do we define apply now that we know the implementation? How do we make a has if a? Well, we need a map in here. And we want some string value. Ideally, it's the string value that represents the type, right? So one might imagine a map that is just, string to hello, and then int to the number 12. Like that is kind of what we're going to have. So how do we get that string? Well, ZIO itself uses a project written by 7Mind. It's called Azumi Reflect. It's very beautiful. It's basically a re-implementation at the value level of like the Scala type system. It's very complex, and it allows certain type relationships to be expressed here. We do not need any of that power right now for this simple version. So we're going to skip that complexity. That's very interesting and complicated. We don't need to worry about that. And we can get away with something much simpler in these non-super polymorphic cases. We're going to use a class tag. Actually, I'm going to make an implicit parameter, implicit class tag. So we're going to get ourselves a class tag. And this comes for free from Scala. This is included, scala.reflect.class tag. It's going to give us a value that we can stringify, basically. So I can make inside of here a new map, stringify the class tag, and then just point that to the value. And it's not tail recursive. I have to say new has in this case. So it knows to not just keep calling this. We want to call this private constructor up here. Should probably make this private too, the whole private dance thing. Not sure if I need this to be private, but I like the way that looks. It's pretty funny. Okay, so now we have this. We can actually just start by printing out the int has just to make sure that that class tag bit worked correctly. So it did. It is exactly what we wrote here. It's a map from the string int to the number 12. We don't have the string and going to hello, but we have this part. And that's what the implementation does. So pretty silly so far. We can also get this bit to work. That works now. Print string has, and these should both appear just fine. Java.lang.string in that case. But other than that, perfectly acceptable. So for combined, I mean, you can imagine how the actual implementation of this is going to do, right? It's really just, if we didn't have types, involved, all we would need to do now is just merge the maps, like, call ++ on map. The only difficulty of this is preserving the information at the type level. So let's think about this. What my first impulse was, probably would have been in basically every case, would be like, okay, let's just let's define a method on has itself. Let's go here and add ++, and that should work, right? ++ of some other b, and then we'll get ourselves a new has that's the combination of them. However, you have to imagine a situation where you also have a third has, maybe a Boolean has. So you have a Boolean has, and I'll make this one that's going to break a double. So what if we call ++ on Boolean has? We want this to be has string with has int with has Boolean. And if you define it on the has itself, the A here is always a single type. It's either always string or always int or always Boolean. And then if you implemented it to accept a second has of B, like that which is a has of B, you're only going to have the Boolean or the int. So you can't get this increasingly composed data type. So it's going to do something that's a little weird that I'd certainly never seen before, but that's pretty clever, which is use an implicit class. So we're going to add an implicit class. We could just call it hasOps for some type. And what that type is going to be, it's going to be any subtype of has. So we're going to add methods to anything that is an intersection of has. So we're going to add methods to this is a subtype of has, this is a subtype of has, et cetera, et cetera. So we're going to add methods to these things. And obviously, these are all subtypes of has as well. So here is actually where we implement ++. And what we're going to accept is our second argument, because you might imagine like having two intersections already that you want to intersect. So a has int with has Boolean with a has, and then ++ that together with its own has A with a has B. So you can't just have a single has type. You want a second, subtype of has. So B is going to be its own subtype of has. So that's B. And then at the end of the day, like looking at these types here, we need a has this with has that. So the way we do that, we can now say has self with B, which is kind of what you have to do to get not the has, you don't want the width on the inside, you want it on the outside, right? It's has string with has int with has Boolean, not has string with int with Boolean, because those types don't make any sense. So the power of has relies on subtyping and adding type information via a big intersection type. It's important to know, by the way, that string with int is a subtype both of int and of string, which might be a little maybe not intuitive. Perhaps it is intuitive. I found that it's kind of like a 50-50 case when showing this to people, where this seems, sometimes you call subtyping narrowing, and this is certainly at least wider syntactically. It takes up more character width than a single type does. But you can think of subtyping as something is a subtype of something else. So this is a subtype of this if you can replace any given B with its subtype. So if A can be replaced, substituted for B, then A is a subtype of B. For instance, this clearly, the subtype has all the power of string, right? It can do anything a string can do. It can do more too. So maybe instead of thinking of it as a sub thing, you could think of it as a specification. It is more specified than this. It's more specific. Not only is it string, but it's string and int. So we require more of it. But a string with int also has a power of int, so it's a subtype of int as well. Okay, so that's an important sort of thing to know. So now that we've combined how do we actually write the implementation? This is the easy part. This almost is like cheating. We need to get a new map that has all the values. So we can call self.map plus that.map. That's great. And then we need to wrap it in has. The only problem with this is that this A is never actually derived really from a value except for an apply. And even then only because we cast it as that. The A isn't in here. So it's all just a fake. This is just a phantom type. This pattern is sometimes known as. We're just storing type information for our own bookkeeping purposes. So what do? We call as instance of self with B. We kind of just lie. We say, hey, this is we want to preserve this information. So now let's try our plus plus. Okay, it compiles, which is cool. Obviously, let's print it out and see and make sure everything is in there. And yeah, we have int goes to 12, string goes to hello, and Boolean goes to true. That's kind of awesome. And it's nice to have this here, but the real reason for this, I mean, is this is combined with the call to get. So we also need to define a call to get in order for this to sort of fully reveal its power. And that also is defined on the implicit class. This will take a type, and then the idea is that you're going to be able to get that type out. But we can't ensure that in every case. But since if the user only uses the exposed API, which when you call apply, tracks the type that you put in, and when you call plus plus, tracks all the types that are in the map, then you can be assured that any type in this compound type exists in the map. So you are allowed to be unsafe. But how do we know when you call get that this type is in the map? Well, that uses the knowledge that we just talked about before, where string with int is a subtype of int and a subtype of string. So has of string with has of int is going to be a subtype of int. And that's the knowledge that we're going to exploit in this case. So let me actually copy paste this up here. So if that's true, then we need to make sure that, so we're going to say we need some implicit evidence that self, which is a has, so it's a has subtype, which might be this thing, is a subtype of has of our A. And then we know we can do this. So if this is our self, a subtype of has, and we want to get a string out, we call get string. In order to know that this is a safe thing to do, we'll need to know that this type is a subtype of, in this case, has of string. So we literally say that self is a subtype of has of A, which will be string in this case. And then we can just get it out. And how do we get it out? This is the easiest thing in the world. We have a function called, we have a map, right? And we can call get, and we can just pass in the string, which, how did we get the string? Well, we need an implicit class tag. We can just throw this in here. And then we can call tag.toString, the same way that we built it, we're going to use it to get it out. Obviously, this is an option of any. Actually, I don't have to call get because I know it's going to be in there. And then I just need to call as instance of on A and lie again. We're lying at this point, but by preserving the information and extensively testing this stuff and making sure that we always use, I mean, you can lie, right? It'll break if you cast one of these hases as something else. It can't prevent you from tricking it. But if the user always uses the exposed API, we're always going to know that the subtype of has describes and tracks the type level what's inside of it. And that means whenever we call get with a type that is a super type of the subtype, it's always going to be safe to call all of this and cast it correctly and all that stuff, which is kind of awesome. And to prove to you that this is working now, let's call this. Well, first of all, this doesn't compile when I call get double. And now this makes sense, perhaps. This kind of ugly, because it gets de-aliased type signature, is saying that double, has of double, it cannot prove that has of double is a super type of has of Boolean and has of int with has of string, because it's just not. It's not a member of this intersection type. Whereas has with int and has with string clearly are. If I show implicit hints, we'll see that it is able to provide, well, both a class tag and some reflective evidence that these types are equal to each other. Let me hide this because it was also showing the implicit class was getting quite noisy. But if I run this, it works. We get out 12, we get out hello. That's has. I mean, that's the core of has. It's like I can make this even less code by deleting the comments, but it's an implicit class, it's a map, and then it really just does this. The only difference in the real implementation are some like performance optimizations and the fact that it's not just using a string here, it's using a value representation of a type, so it can do fancier, higher kinded things rather than just these monomorphic types. But it's surprisingly simple, but also I thought it was really cool. I didn't know you could make an implicit class on subtype constraints and then do this fancy stuff. I mean, very, very clever. I mean, I guess it makes sense, but a novel intersection to use these techniques. And from my perspective, like this is what I like about ZIO so much, is that it is willing to do hacky things, right? That maybe this feels hacky to you. We're calling as instance of everywhere. It's willing to do that in order to get a really nice API. It's a library that generally understands the trade-offs of usability versus purity at all levels. Because you could do a similar thing with like a heterogeneous list, and then you wouldn't maybe even have to call as instance of, maybe in Scala you do, but it feels more type safe. It might feel more type safe, but it's actually like about 1,000 times more frustrating to use. You need it in some situations, but this is the most elegant thing I've seen. There's nothing like this in Haskell. A lot of Scala constructs are sort of stolen from Haskell, but since Haskell doesn't have subtyping, you can't do this trick. I'm sure there are other tricks you could do. But yeah, I thought this was a very sort of Scala first way of encoding something that is also a solution to a very practical problem. So I will stop my rambling there. And we have 3 minutes and 20 seconds left before I'm kicked out of this Zoom room. So any questions? Did this all make sense? Was that neat? Did this make you tired? I know it's early for some of you.
Probably more of a comment than anything, but you mentioned quite a few times that you're lying when saying as instance of. It's not actually true. You've said that the underlying map is a map of string to any, so we need to necessarily cast it to get any information about what it actually is. So you are telling the compiler the type of it, and you are correctly telling the compiler the type of it. So you're giving it a hint rather than lying to it.
That's a good point.
But the other thing that I'd point out is your a parameter on the has is phantom type, and something that I didn't really understand type level programming until I understood this. You can put whatever you like if you're not using it as anything other than a phantom type. So you can't really lie about what that is, because that is whatever you tell it to be, which is why it works with casting in the implicit, like in the plus plus, which is kind of a cool thing. It's a neat little trick that you can have these type parameters that don't actually, they never exist at runtime. So you can always cast to whatever you like, as long as you are certain that it is sound. So I guess all of this stuff is type safe, but only because of the way it's put together. If you allowed people to mess with these and create their own constructors and things like that, then it would very quickly not be type safe. I guess it's type safe in the API and not type safe anywhere else, which is actually how the ZIO core interpreter works as well. I think it starts off with null as instance of something or other, which is kind of amusing.
Yeah.
Anyway, that's my little rant.
No, I totally agree. I think in terms of lying, it's sort of an intuitional, it feels like almost cheating. It feels like I felt when I was doing, ooh, this feels cheating. But yeah, no, it's as long as we're tracking real information that's meaningful to us. It's just sort of disjoint from the usual steps of having the compiler correct you. You're telling the compiler something. So it kind of, you've got to take on the responsibility of being correct. I'm speaking quickly, or more quickly than usual, because we've got less than a minute. So if we get kicked out, you could probably join the same link that I posted. Hopefully that still works. Otherwise, I'll post a second one right after that. But may as well just sort of meditate while it dies, so no one's cut off, or shout random things, or drink LaCroix. Cheers.
Thanks a lot. That was great.
Awesome. Yeah. I thought it was very cool. Reading the ZIO code base has many secrets, many interesting things in there.
About to have more interesting things too with the 2.x.
Yes, we're shoving lots of fancy tricks in there. I feel like the less than a minute is always more than less than a minute. I think they